forward this just in case anybody wants to watch it later. So let's go to, I forget what this one is. Sometimes I don't need them. Okay. Two or more expressions joined by an inequality sign. It's called an inequality. No wonder we skipped it. Okay, number 3. An inequality in the form A is between x and, or x is between A and B is called, okay, I called it a double. It's also called a compound. Compound or a double. It's just, I've used the word double in a lot of previous classes that I've taken, and so I'll just blurt it out as a double because there's two inequalities. So this is a compound or a double. And later on, you're going to see when you operate algebraically on a compound inequality, you have to treat all three sides equally. Like here, when we have this, we multiplied or divide, add, or subtracted on both sides. Now, I would say in the vernacular, we would operate on all three sides. Because I'll show you what I mean. Let's say I had to solve this. I'll make it so there's no fractions. So the first thing I would do is subtract 1 from all three sides. So I subtracted 1 from here. I subtracted 1 from, or not subtract. What am I doing? I don't want to subtract. I want to add, right? I want to add. I better write it out so I don't screw it up. So minus 2 is between 2x is between minus 2 and 6. And then I divide everything by 2. Since it's positive 2, everything stays the same direction. So it's minus 1. X is between minus 1 and 3. That's the solution to the original compound inequality. Because we want to spot, well, where's x? If 2x minus 1 is between these two numbers, then where's x? Well, x is between negative 1 and 3. Inclusive. Inclusive. When I say the word inclusive, that means include the inputs. Okay? So that's what I mean by we do the same operation on all three sides. So the first operation was add 1. The second operation was to divide by 2. Okay, so that's compound inequality number 4. When solving inequality, if you obtain a statement that is always false, such as 4 is greater than 12, the answer is, what would you, now we were studying equations before. What would you think the answer is here? Based on what we did with equations. If you get a false statement. No solution. Because the same thing algebraically can happen when you're dealing with inequalities. There's no rationale for why an inequality should have a particular solution other than what you actually generate. Just because somebody wrote an inequality, just like an equation, there's no guarantee that it's written accurately. When solving an inequality, if you obtain a statement that's always true, such as 6 is greater than 4, then the solution is, see what they're driving at is that all the variables vanish. So if you get a true statement, all real numbers. All real numbers, yeah. All real numbers. Okay? So it's very similar. Now you notice the true statement we had with an equality was that 4 equals 4. A true statement on an inequality could be 6 greater than 4. It's still true. But 4 greater than 6 is false. Right. So you just have to look at it as an inequality, not as an equation any longer. Number 6, when both sides of inequality are multiplied or divided by the direction of the inequality is inverse. So when do we reverse it? Negative number. Good. Just hammering it home. This is like review stuff. To indicate the solution set of x greater than or equal to negative 1 on the number line, what kind of circle do we draw? This is called an open and this is called a closed. A closed, right. I call it a dot. Circle dot. They call it open and closed circles. Okay, so see, it's all terminology. It depends on who wrote the book and when they wrote it. And then number 8, To indicate the solution set of x less than 1 on the number line, draw an open. Okay, so we got that hammered home. We're not going to miss that. So now we have 6 possible choices. Let me point out that choice C is all reals. It's a solid line that just goes both directions infinitely. So it goes from minus infinity to plus infinity. It's the whole number line, so it's all reals. You'll notice that number B has no dots, no circles. So there's no solution, no real number. So this is all real numbers, no solution. They always put those in there as distractors. So we want x greater than or equal to positive 2. So we can eliminate. Okay, I was going to say we can eliminate A and F because they have circles. It has to be the dot, E or D. Now, if you're not sure, you can plug in a number that's not equal to 2, usually 0. If I plug in 0, I get a false statement. So I can't use 0, so it has to be this one. If you're not sure, greater than's to the right, less than's to the left. So that's another way to do it. But you have to figure out a way to remember for yourself. Okay? And by the way, you always look to see what they're specifying as the solution. It's a real number, because later on they're going to have solutions that are integers only, the lattice points. The lattice points on a number line are just the integers. See, these are the lattice points on a number line. And it's possible they'll say, okay, integer solutions only. So when we get there, make sure I'll point it out to you so we don't miss that. So now we have x plus 8 is greater than or equal to 1. So what's the solution for x? What do I need to do to both sides of the equation to solve for x? If it was not an equation, if it was an equation, what would I do? Transpose the 8 or subtract 8, right? So that's the same thing you're going to do now. So what do you get? X is what? Greater than or equal to -7. So you can eliminate, see, B and D you can eliminate, because we do have a solution, and it's not all real numbers. So is it open or closed? Is it a circle or a dot? It's a dot, right?
Yeah, it should be closed.
Yep, it's close. So it's either A or F. So it says greater than -7. So it's F.
The arrow's pointing down.
Yeah. So if you don't see it right away, because some people get these right away, if you don't, you can eliminate quite a few of them just by being.
Well, the trick that I learned, and I don't know if it works for everything, is the way that the arrow's pointing in the problem itself, and the way that you need to go.
As long as X is on the left.
Yeah. Else you have to go in the opposite direction.
Yeah, if X is on the right, then you have to reverse everything, because you have to read from the variable. Okay. So what do I do to this one? Who wants to grab this one?
Add 4 to both sides.
And so what's your solution?
It's going to be positive 2.
So X greater than 2.
Than 2.
So which one is it?
So it's got to be the open one, not the closed one.
Right.
So it's A.
A. Good. I think you're catching on. Number 15. Okay, now we have a fraction. See, negative x divided by 9 greater than or equal to 2. If you guys got pencil and paper, you can do them on the side, because that's what I'm doing. Now you could do this in 2 steps or 1 step. You see, this is -1/9, right? This is how I do this. This is how I look at this. Well, this is how they wrote it, but this is what I see.
Mm-hmm.
So if in 1 step, what can I do? We're real simple in 1 step. Multiply by what?
By 9 on both sides, no?
Which one?
By 9.
I want to get rid of the negative too.
Oh, so it would be -9?
Well, yeah, these two now, when I multiply them, I want +1.
Okay.
If I multiplied by 9, then I'd have to do another multiplication by -1.
Okay.
So why not do them both at the same time? See, these multiply out for 1. And this gives me -18, but what else do I have to do? I'm multiplying by, I have to change the direction. Because I multiply by -9. Okay? All right, so x is a real number. Now you see some of the distractors, they're giving you lattice points where integers. So we can eliminate D and E, B and A. So it has to be either C or F. And so x is less than or equal to -18, so it has to be C, right? Because D says, or F says that it's greater than or equal to -18. But it's less than or equal. We okay? Yeah, okay, good. That was 15, 17. 6x plus 7 is greater than or equal to 13. So it's a two-stepper. First thing to do is subtract 7 or transpose the 7. And then divide by +6. So the direction of the arrow is never compromised. It always stays the same direction. First thing we did was subtract, which keeps it the same, and then we divided by +6, which keeps it the same. So x is greater than or equal to 1. So it's a dot. Now, the thing here is that the tick marks, the lattice points are only the even integers. And our answer is an odd integer, so we're going to be between them. We're going to be between 0 and 2. You see that? So C is the right answer. Yeah. We're halfway between 0 and 2, which means +1, and it's a dot because it's inclusion. Good. Number 19. Okay, so now I got something that looks like one of the equations we had earlier yesterday. So these are real simple. You just treat them like an equation. Now remember, I have a choice which way to move my x's. You see, if I subtract 3x, I'm going to end up with negative x's. I'd rather have positive x's. So it's my choice because I'm doing the problem. I'm going to add 6x, which means I want to get rid of this. So I'm going to add 48. So these vanish and these vanish. And since I'm adding the same thing to both sides because these are equal, I get 9x. Arrow stays the same direction. So I get x is greater than or equal to 6. See, now I don't have to worry about multiplying or dividing by a negative number. You see why I did it that way? Now you could do it the other way. I'll run through it with you, and I'll show you what happens if you do it the other way. Some people have a mind that says, no, I'm going to move everything to the left. So they end up with -9x is less than or equal to -54. And now when you divide by -9, you do get x, but you have to change the direction. And when you divide this by -9, you get +6. So you still get x is greater than or equal to 6. And you can see why you always have to read from the variable. Because saying that x is less than or equal to 6 does not make any sense if you think about it. Because we're not interested in 6, we're interested in x. All right, so which one is it? X is greater than or equal to, it looks like F again. See, they put a lot of distractors in there for you. This time they used integers instead of even integers. They used all the integers. It looks real busy that way, doesn't it?
It does.
Yeah.
It makes it look a little more overwhelming.
I'm sorry?
It makes it look a little more overwhelming because there's so many numbers in there.
Yeah. Okay, this one's a compound inequality. We don't have to solve it. It's already solved. It's already x. But we have a circle on the left and a dot on the right. So it's between them. It can't be B, A, B, or C. And it can't be D because there's no solution. So it's between E and F. So on the left is where we have the circle, so it has to be E, right? And once again, it's even integers, so this is -1, and that's +2, so. And on the face of it, with all those possibilities, it looks overwhelming. But if you just focus on what you need to focus on, see, I eliminated 4 of them right off the bat. So then it's a choice between only 2 of them. Right. Then it's a matter of making the right selection for where's the circle, where's the dot, which way is it open, which way is it closed. All right, that was 26. Okay, now they're going to move to these integer solutions. You see what, now you have to make sure you spend the extra couple of seconds reading the problem, see where x is an integer. So A, B, E, and F, it has to be between C and D because it's an integer solution. So we want x greater than 12, which means what's the next biggest, if it can't be equal to 12, what's the next integer greater than 12? Just add 1, 13. So it has to be 13, 14, 15, 16. So you could say x greater than or equal to 13, 14. So it has to be C. Because D is going the wrong direction. That's less than 12. Because 11, 10, 9, 8 are less than 12. Okay, so make sure you check. And if you, now look, number B is for real numbers. It's the right solution. If it was where x is a real number, that would be, if you pick B and it says it's wrong, then, oh, reread the problem. Oh, it's an integer, so it has to be one with only dots or lattice points, whatever you want to call them. Okay? On a test, if you miss this one, the best I can do is give you half the points. Okay? So, and there's going to be a couple of them on the test, so be heads up on that. Number 33, another one of these. Okay, so minus 4x is less than or equal to 24. So negative 4x is less than or equal to 24. So I'm going to divide by negative 4, right? Or multiply by negative 1/4. Because now I get x. And here I get negative 6. But what has to happen? Switch the arrow. Now this is in integers. So I'm including negative 6. So negative 6, negative 5, negative 4, negative 3. Because I'm greater than. So which one is it? F. So you see, you could eliminate A, B, C, and E. And then it's just a question of making sure that your arrow's in the right direction. Because if you didn't flip the arrow, you would have picked D. So I think there's maybe 1 or 2 more. Let's see, 37. Okay, minus 25 is negative 25 is less than minus 10. All right, so watch how I do this. I'm going to add 5x and add 25. This is how I am. See, I don't want a negative coefficient. I want a positive 5x, and that way I don't have to worry about. That way I don't have to worry about the arrow. That's just my way of thinking. Because I would have to move. Well, I would only have to move one of them. See, okay, maybe let's see how the other it works the other way. If I just add 10 to both sides, then I get negative 5x is greater than negative 15. And when I divide by negative 5, the arrow changes direction, so I get x is less than 3, which is what we got here. Okay, so it doesn't matter which way you do it, and this is integers. So if it's less than 3, then it's 2, 1, 0. So it's E, right? Because we're not including 3. It's less than 3. So that's why. And then see, this is the extraction for all reals, and that looks really good, less than 3. And people do this so fast, and I every time on a test, people miss points. I hate that. I point it out and I say, be careful, but people work real fast, I guess. The mind just. Okay, now we have a double inequality. But notice that it's a negative x. So it's stylized to make it look like it's done, but it's not, is it? It's 3 is, you can tell the way it's written that it's wrong. You would never have it pointing, it's pointing the wrong direction, but the reason they did that, I'll show you why in a few minutes. If I just multiply through by -1, all the signs change. And so do the arrows. Right? If I multiply through by -1, every sign changes. So this becomes a negative, these become positive. But since it was a negative, the signs have to change direction. So there's my answer. And now it's in the logical fashion. The reason they gave it to us this way is because if I wrote it the other way, x greater than or equal to -2 and less than 3, and then I multiply negative x. Then I multiply through by -1, I would have 2 is greater than or equal to x is greater than -3, which is what I have here, but it's written backwards. So they wrote it to start backwards. I'm sure there was a big discussion in the room with the professor and the people who were writing this. Should we start it backwards? Because if we start it forwards, they're going to end up backwards, and then they're going to get all confused. So which one is it? It's integers. So here's a way to do this. We're not including -3, so it's -2, -1, 0, 1, 2, because I include 2. So that's it. That's the answer. It's those 5 numbers. Which one? E. E. Good. Sounds good to me.
Sounded good to the computer too.
I'm sorry?
I said it sounded good to the computer too.
Yeah. I love the little messages they do. So that's it for inequalities. It's what's really going to help us now is when we work on inequalities in 2 variables. Inequality in 2 variables will describe a line with a half plane. Like, how can I, here, watch. Everything jumps up a dimension, 1 dimension. So if I have x is greater than 2, then in 1 dimension, which is the x-axis, I would have this. In the plane, if I had the line x is greater than 2, then it would be, instead of just being on the x-axis, it would be a dotted line. It would be a half plane. Because see, y is not involved here, but if I want to draw it on the plane, then it's a half plane. Here it's a half line. Because if you just think about it, if this is the x-axis, that's all we're doing is just dealing with the line itself, the axis. But if you expand the axis to 2 dimensions, now you get the whole half plane. So that's what happens when we're dealing with inequalities in 2 variables. We form the line associated with the equation, and then pick which half of the plane we highlight as a solution. And so we're going to do that Thursday with 2 variables. But it's very similar. I didn't write the y here. Sometimes I get too fast. Right, this is the line x equals 2.
Right.
So if we were to draw a line x equals 2 in 2 dimensions, it'd be a vertical line. But if we say this is an inequality in 2 dimensions, then it becomes a dotted line. See, in 2 dimensions, this becomes a dotted line or a dashed line, and this becomes a solid line. Because here we're including the line, and here we're excluding the line. Here we're excluding the point, here we're including the point. See, because there's only 1 point involved, because the line just crosses the x-axis in 1 point. But in the plane, it's a line. So, but it's a line that you can't see. So you make it dotted instead of writing a whole bunch of little circles. Anyway, that's where we're headed with that. You'll see it again later on Thursday. So that's it for this section. What we're going to do is switch gears, and we're going to go to. Does anybody need a break? So I just keep going. We're going to go to system of equations. So we already know about equations in two variables, linear equations. And we know that they can be written in standard or general form. We know we can solve this, right? We can solve, remember I can just do this. By equals minus ax plus c. I just subtract this. And then I divide by b. I would get y equals minus a over b, x plus c over b. And I would call this m and call this little b. And we would end up with y equals mx plus b. So we can change this to this. And whatever this turns out to be, we call that m. And whatever this turns out to be, we call it little b. And this is the slope. And this is the y-intercept. 0b. So when x is 0, you get y equals b. So this has a lot of information inherent in the way we write it. It's our favorite. The slope-intercept form is usually the most favorite. The general form is kind of it's stoic. It's like perpetual. It's like poetry or something. So what we have then, when we have a system, usually the system, we use this form just to illustrate it. And we have two equations. We have y equals m1x plus b1. And we have y equals m sub 2x plus b2. So we call this line 1, and this is line 2. This is the preferred form because this one, we can algebraically manipulate that to get here. So this is more usable because now I can discuss this in terms of m and b. And if m1 is different from m2, then the lines, graphs, intersect in one point, the point of solution, the contingency point, right? If m1 is equal to m2 and b1 equals b2, then L1 is equal to L2, infinite solutions. It's the same equation, right? If these two are equal and these two are equal, it's the same equation, so it's the same line. So I have infinite solutions because they overlap. They overlap everywhere. So every point's a point of intersection, so there's infinite solutions to the system because the system is degenerate or dependent. And then if M1 equals M2, but B1 is not equal to B2, then no solution. Parallel lines. That's the railroad tracks abbreviation. Parallel lines. So there's your three possibilities. And you see, they all rely on these numbers. So as soon as the slopes are not equal, I know they intersect somewhere. And we're not talking about the special lines. The special lines you could tell right away because two horizontal lines are parallel and two vertical lines are parallel. And a horizontal, there's always a horizontal and vertical line out at any point. That's described on number 1. Every point has a horizontal and a vertical line passing through it. The line x equals a and the line y equals b, if the points a comma b. So we're not talking about the special lines. We're talking about lines that aren't parallel or perpendicular to the axis. They're not those special ones. These are just any old lines. And so these are the three things that will always hold. One solution, infinite solutions, no solution. Now, we can do this graphically depending on if there's lattice points where they cross when we graph them. And so they introduced that as a starting point. But after we do that, then we're going to solve them algebraically. We're going to solve where they intersect algebraically. And so if we do it algebraically and the x's and the y's don't vanish, then we have this situation where there's one solution. But if the x's and the y's vanish, it's because they have the same slope. So in this case, in either one of these cases, the x's and the y's will both vanish, and we'll either be left with a true statement, which means it's same line, infinite solutions, or a false statement, which means they're parallel lines because the slope or the intercepts are different. The y-intercepts aren't the same, but they're parallel lines because they have the same slope. Parallel lines have the same slope, right? So a lot of this is straightforward, but I thought I'd introduce that so when we get started here. So we're going to start with the definition of a system, et cetera, et cetera. Let's see what happens here. When two or more equations are considered simultaneously, like I got up there, L1 and L2, the equations are called a system of equations. So that's a system. So for two equations, you need two variables. For two variables, you need two equations. If we had three variables, we would need three equations. Four variables, four equations. Okay? The ordered pair or ordered pairs that satisfy all equations in the system are called what? Solution. Yeah. They're the solution. They're what makes it true. A system of equations has no solution, and it's called, I think I mentioned it, it's on your printout. It's inconsistent. If you look on the second page, the two that are parallel, it says inconsistent. Now, on one variable, we call that a contradiction because we end up with a false statement. Here we end up with a false statement, but in terms of a system, we call it an inconsistent system. We don't call it a contradiction. We call it an inconsistent system. There's no consistency to it. Any system with a solution is called consistent. The ones that have one solution are called independent, and the one with infinite are called dependent. But they're both consistent. It's just that they're different from the inconsistent words. A system of equations that has at least one solution is called consistent. If it has one solution, it's independent. If it has infinite solutions, it's dependent. A system of equations that has an infinite number of solutions is called dependent. These are all written down for you, so you can always look for them. If the graphs of the equations in a system of linear are parallel lines, then the system has no solution because they don't intersect. Right? They either intersect in one point because they cross, or they intersect everywhere because they're the same line, or they intersect nowhere because they're parallel. That's the only three possibilities for lines. I showed you about the planes. It's the same notion. It's amazing that happens no matter what the dimension is. I think that's truly amazing for mathematics. That's just me. That's just me. All right, so that was 6. 7, if the graphs of an equation of a linear system intersect at only one point, then the system has only one solution. That's the solution, that point. It's called the simultaneous solution. And number 9, when solving a system of equations, if a true statement such as 0 equals 0 or 6 equals 6 is obtained, the system is dependent, and we know then that it has an infinite number of solutions because they're the same line, they intersect everywhere. And just driving this home, ain't I? But if it's a false statement, it's inconsistent, then it has no solution. Okay, so just repetition here. All right, so now here's a system. It can only have one unique solution. You see, the slopes aren't equal because the top slope's 4, the bottom slope's -1. That's the first thing I noticed. You see, so they intersect somewhere. So there's only one solution. So that solution has to solve both equations simultaneously. So if it doesn't solve the first equation, just move on because it doesn't matter if it solves the second one or not. It has to solve both of them. All right, so if I plug in 2 for x, I get 8 minus 5, 3 is 5, so it's not -5, so I can move on. Now I plug in x equals 1, I get 4 minus 3 is 1, so that doesn't work. And last one, if I plug in 5 for x, I get 20 minus 3 is 17. So it works in the first one, and now if I plug in 5 in the second one, I get -5 plus 22 is 17. So that's the solution. It satisfies both equations simultaneously. Now here you can only have either one or none. They give you 3 choices. At most, one could be a solution because they have different slopes, like I said. You can't have 2 or 3, but you can have none. Yeah, they may pick 3 points that are just, who knows, they're way off in space somewhere. Okay? Number 15. Okay, now we're going to do these by graphing. Now you see why we did the drawing yesterday, because these are easy equations to graph. See, slope intercept. See that? Okay, so but I got to draw 2 of them. And so the top one, the intercept's -4, and the slope is -1. So I go -1, 1. And then I do the line tool again, and then I go -6, and now I have a positive slope. So up 1 to the right 1. And look, I have the point of intersection. These are going to have lattice points for intersection because if they intersect off of a lattice point, then you have to guess what the fraction or decimal might be. And that's not, they don't want us to do that. So these will always be lattice points. So first of all, they're going to ask us to check the graph. So we have the right graph, so we know that the solution is x equals 1, y equals -5. And if you don't believe it, you can just plug them in. If I plug in 1 for x, I get -5, -5. So it's 1, -5 solves both of them simultaneously. So don't forget your parentheses. If you don't put the parentheses, it'll mark it wrong. All right, so it's kind of misleading because if it's not a lattice point, then there's no way for me to really hit it on nail on the head because then I have to guess. Is it a third? Is it a fourth? Is it 2/5? You know, it all depends on how good the drawing is. So these are set up structurally so that we don't have to do that. Thank God. At least so far, I haven't found one that does it. 17. X plus 3y equals 2, 3x plus y equals -2. All right, so now I got to plot points. See, this one's not set up in the y equals mx plus b form. These are set up in the general or the standard form, right? So what do I do here? Well, I can pick one intercept. If I let y be, for the first line, if I let y be 0, then x is 2. Because 2 plus 0 is 2. So 0, 2, I'm sorry, 2, 0 is 1 point. So there's 1 point. Now I just need a second point for the first line. So why don't we let, let's see, what's an easy one to do? If I let x be or y be equal to 1, then to get plus 2 on the left, I need x to be minus 1. So we already know we can do one of the intercepts. If y is 0, then x is 2. Now let's let y be 1. So I have x plus 3 equals 2, so x is minus 1. Okay, I can't force both of them to be intercepts, because if I put x equals 0, I get y equals 2/3. And I can't really put 2/3 on. I have to have lattice points. So we said -1, 1. So -1, +1. That's the first line. Then I hit the line tool for the second line. Once again, I can let x be 0. See, if I let x be 0, then I have the intercept -2. So now let's let x be 1. So now I'll have 3 minus y equals -2. So minus y equals -5, so y equals 5. So if I plug in 1 for x, I get 3. If I plug in 5 for y, I get 3 minus 5 is -2. So there's my 2 points. So I always try to get one of them to be an intercept if all possible, and then I have to choose a value for one or the other. Usually choose the value for the one, whichever is easier. You get a hang of it after a while. So the intercept's 0, -2, and the other point is 1, 5. Oop, they don't intersect in a lattice point, do they? Okay, something's wrong. Oh, I see what's wrong. I got minus y equals -2. This should be +2. See, I dropped that minus sign. I just went y equals -2. It's minus y equals -2, so y equals 2. So I'm gonna move this up. I can do that. Just move it from there to there. So my intercept is +2, but the 0.15 is still correct. But they still don't intercept in a lattice point. Let's see if the other ones. If I let x be 1, yeah, that's correct. 1, 5. Do I have the right point? Yeah, 1, 5. 0, 2, and x is 0, y is 2. I know something's wrong here. See, it's incorrect. What did I do wrong? Let's see if we can figure out what I did wrong. Did I copy the numbers correctly? Oh, it is plus y, so that's what's going on. This minus should be a plus, so that's what's wrong. So let me get rid of that. Yeah, so this changes everything. So it is -2. But when I go to solve this, it's plus y. So you get y equals -5. There we go. So when x is 1, I get 3 plus y equals -2, so y equals -5. Sorry about that. So what I can do here, since this is still hasn't been set, I can move this down to there, and I can then go 1, -5. So this should be down here. There we go. And now you see they intersect in the lattice point, so that makes me more happy. Okay, so we have the right lines. We have the right system. And the intersection point looks like -1x plus 1y. So -1, 1. So I didn't do that mistake on purpose. It's just because I wrote the wrong symbol here. And then I made a mistake, corrected it with the wrong symbol, and then I had to review what I wrote and said, oh, I messed up originally. So my second mistake just compounded the whole thing. I apologize. See, you guys thought I didn't make mistakes. It happens to the best of us.
If you make mistakes, then they won't be so hard on myself.
I know, right? Yeah.
Yeah, be easy on yourself.
I'm still learning that.
All right, so once again, this is graphing, and you kind of know what to expect because I already told you that it's a lattice point. Solve the system of equations graphically. Okay, so y equals 2/3 x plus 1. So that's easy. That's slope or point slope. So for the first line, the intercept's plus 1, and the slope's 2/3. So I go up 2 to the right 3. Up 2. Okay, so there's the first one. For the second line, I'm going to need 2 points, right? 2x minus 3y equals -3. I guess you can see why it's preferred to have equations in this form. This form requires more effort. Now, there's an alternative. You could do this. We could just go ahead and solve for this form. So I subtract 2x, right? Move that over, 2x. And then I divide by -3. So I get 2/3 x plus 1. Right? If I divide by -3, x.
Right.
So they all become positive. So 2/3 x plus 1. Hey, it's the other line.
Yeah.
So they're the same line. See, now, we could have tried to find 2 points for that. What we did instead was to change it from this to this by just doing the algebra.
Okay.
Remember, this is symbolically, this is specifically for the values that we have. So A is 2, B is -3, and C is -3. And this is what it turns out to be. Now, the other way to find 2 points, you would end up with the same line if you did it correctly. All right, so then what's the answer? Infinite many solutions. So it's C. Okay? So now we're going to solve algebraically, I think. To solve it by the substitution method. Okay, can I erase this?
Yeah.
I think some of this is on the handout. I'm pretty sure, isn't it? System of equations. G, system of equations. Yeah. Okay, so here's what we're going to do. We got y equals -4/5 x plus 5. And then we have the second equation is x plus 10y equals 15. So they want us to do this by substitution. There's 2 methods algebraically that are used, substitution and elimination. They're pretty close. Substitution, see, I already have what y is. This is y. I can just plug it in right here and substitute it. So if I write it, I'll just get rid of the y's. So I have 10 times y, and y is -4/5 x plus 5. Equals 15. So x plus 10y equals 15. So now I've eliminated the y's by substitution. So now I just have to distribute this. So this will be a minus, right? 4/5 times 10 is 8. 8x, right? 40 over 5. And then 10 times 5 is 50. So I got -7x equals -35. I'm subtracting 50. Am I going too fast? And then I divide by -7, so x equals 5. So I have x equals 5, now I got to solve for y. So I plug it back into where I substituted. So I have y equals -4/5 times 5 plus 5. Well, the 5's cancel, I get -4 plus 5 is 1. And then I check in the second equation. 5 plus 10 times 1 is 5 plus 10 is 15. It checks. So my solution is 5, 1. You see how that works?
Yeah.
So you take the first equation, substitute it. It's automatically set up because it says y equals. So I just plug it in right there, and then I solve that for x. I put that back in here to solve for y, to see what, because I know that y is dependent on x, so there it is. And then I use the second equation to check my answer. Because I know this will solve the first equation, because that's where it came from. But will it solve the second equation? And it did. So it's my solution. So 5, 1.
Somehow your camera keeps losing connection.
What's that?
Somehow the camera keeps losing connection on the board.
Oh, it does?
So for a minute it'll be there, and then all of a sudden it's gone.
On the blackboard?
On here, like,
Oh,
and it comes back, and it like goes, and it comes back. That's why I keep looking up and looking down.
that might be their problem. Because it's okay here.
Right.
Is your battery hot?
No. What it loses is the camera over here that's showing where you're doing the math. I can see if I go here, I can see what you're seeing there. But if I click on it again, it sometimes will show me what you're doing there.
Well, I'm not changing it here, so I don't know how you're doing that.
I don't know what it's doing, but it's not catching the camera all the time.
Oh, okay. Well, that's interesting because I didn't know that happens. So any questions about this? So this is called substitution. Let's see, 31. I'm going to do a few of these. See, this one's set up for substitution again. Can you see it? The second equation says y equals. So it's already set up for me. I don't have to do any manipulation. So I have x minus y equals -3. Then I have y equals 2x minus 1. So if I just plug this in right here, I get x minus 2x minus 1 equals -3. So distribute the negative through. So you get -x, that becomes -1, so it's -4. So x equals 4. Plug it back in here. So y equals 2 times 4 minus 1 equals 8 minus 1 is 7. And then plug 4 and 7 into here to double check. So 4 minus 7 equals -3. So my solution is 4, 7. I don't know if that's too fast. I see these as straightforward. They're not terribly difficult. And the reason we need to do this is because sometimes graphically we won't have a lattice point on our future problems, maybe one or two of them. If they turn out to be lattice points, we go ahead and use them. But if they're not, then we have to actually figure out where the intersection is. Because the intersection or the vertices are where we're interested. Let me get the linear programming. So we said 4, 7?
Mm-hmm.
Okay. 3x plus y equals 15. Okay. I see something happening here. 3x plus y equals 15. X equals minus 1/3 y plus 5. So this time we have x. So we plug in 3 times x, which is minus 1/3 y plus 5 plus y equals 15. So we get minus y plus 15 plus y equals 15. When I add the y's together, I get 15 equals 15. Same line. Same line. So it's a dependent system, B. See, my variable vanished, and I ended up with a true statement. Yes? If my variable had vanished, then I had 15 equals 10, 15 equals 0, then it would have been no solution, it would have been parallel lines. Okay. 35. Okay, now we're going to try the other form, which is elimination. I like elimination a lot better. You'll see why. This problem is real easy for elimination. It's set up for us. I wish they were all this way. What we look for in elimination is the same coefficient on the opposite coefficients. You see how plus y and minus y? Just add the two equations. You get 5x equals 15 because the y's vanish. Isn't that easy? Mm-hmm. All right, so x equals 3. And now what I do is I just pick the first equation and I solve it for y. So y equals 4. And then I check in the second equation. 4 times 3 minus 4 is 12 minus 4 is 8. Check. So the solution is 3, 4. I like elimination. My buddy that used to teach here used to tell people, just use elimination. Don't use substitution. I think they're both valuable at times. It all depends on how the problem's written. This one's set up. You either look for opposite signs, and then you can always change the coefficients, which is coming up, or you look for the same coefficient and you can change the sign. So either way. So for this one, the solution was 3, 4. Okay, so parentheses 3, 4, and let's see, that was 35, 41. Okay, you see, this one's ugly. 5x minus 7y equals minus 37. 3x plus 2y equals 15, right? All right, so the best I have here is these are opposites. So I'm going to multiply the top equation by plus 2. You can multiply equation by any number. It doesn't change anything. It just changes what it looks like. It doesn't change the solution. So I got 10x minus 14y equals minus 74. I'm going to multiply the bottom equation by, who can guess?
The same thing.
No, by 7. I get 21x plus 14y. See, the reason is I use the y's is because they're already opposite signs. So I just change the coefficients to be the opposite. And then I get 70 plus 35 is 105. You guys do the arithmetic like that? I always do tens first. 70 plus 35 is a lot easier. Carry the 5, add the 3. All right, so now now I'm right here. This is where we started. I had to do a preliminary to get to here. It's the same place, essentially. And so these add up to 0. I get 31x. And I get 31. So x equals 1. Anytime you get an integer, if you don't get an integer, you know for these, something's wrong. Although on a test, if it's non-graphical, they may give you easy fractions like halves or fifths, tenths. Not 37ths or 83rds or 113ths, but something simple. All right, so x equals 1. Now, I got to go back to the original two equations. It's not here, but I got to go back here. So I take the first equation, I put in x equals 1. So I have minus 7y equals minus 42, so y equals 6. So now I put these two values in the second equation, so I get 3 plus 2 times 6 equals 3 plus 12 equals 15. So my solution is 1, 6. That's where the original two lines cross. Now, as far as slopes, I know they have different slopes. Here's the easy way to do the slope. You take this number and divide by the opposite of this number. So it'd be minus 7 over minus 5. The slope is 7/5. This slope is minus 2/3. Since they're not equal, I know they intersect. You always take this coefficient and divide by the opposite of this coefficient when they're in this form. It's pretty simple. So what's the slope for 3x minus 2y equals 7? It'd be minus 2 over minus 3, so 2/3. That's a quick way to just by inspection, when you look at two equations, then you can figure it out. See, the slope here is minus 1, and the slope here is plus 1/4. So they're not equal, so they intersect, which you already know. So we said 1, 6, right? Okay, 1, 6. All right. I'm doing good today. Very few. I made some mistakes. Let's just look at this one real quick. See, this one's written backwards. And this one's going to be dependent because, look, if I multiply the top equation by 3, I get 15x minus 12y equals 9. If I add them together, I get 0 equals 0. See, just by inspection, you can tell. But that's a homework problem, probably. 46. Okay. 4x. See, when they're set up like this, they're almost automatically elimination. It's just a question of which variable you want to eliminate. And for me, you see how simple this one is? I just multiply the top equation by 2. And I'll get 2y. So if I multiply the top equation by plus 2, I get 8x plus 2y equals 14. I just add the bottom equation. Uh-oh. I get 0 equals 33. So no solution. Inconsistent. They're parallel lines. Now look at the slope here. The slope is minus 1/4, and here the slope is minus 1/4. It'd be minus 2 over plus 8, so that's minus 1/4. They have the same slope. That's why they're either same line or parallel. So no solution. C. Okay. And here's one with a fraction, just to show you. Then I'm gonna show off and do show you how we would do it in modern day with modern day machinery, which is the calculators that I gave you, as a matter of fact. Okay, so 3x minus 2y equals 5, and 2x minus 3y equals negative 2. So now these are both positive and these are both negative. So I'm going to have to multiply by a negative, one or the other. So which one do you want me to get rid of, the x's or the y's? Let's get rid of the x's. So I'll multiply the top one by plus 2. So I get 6x minus 4y equals 10. I'll multiply the bottom one by negative 3. So I get negative 6x plus 9y equals 6. Right? So that gets rid of the x's. So I have 5y equals 16. So y equals 16 over 5. So this won't happen to you on a test or on homework. But I wanted to show you one so you can see that it'll still work. So I have y equals 16 over 5, so I take the first equation. 3x minus 2 times 16 over 5 equals 5. So That's 32 over 5. And what I'm going to do is just change this to fifths. It's 25 over 5, because I know I'm going to be adding them anyway. And so when I move that over, I get 3x equals 57 over 5. And when I divide by 3, I get 19 over 5. 3 times 19 is 57. So I divide both sides by 3. So there's my answer. Now I check in the second equation. 2 times 19 over 5 minus 3 times 16 over 5. That's 38 over 5. That's minus 48 over 5, which is minus 10 over 5, which is negative 2. Boom. So my answer is 19 over 5, 16 over 5. Or, if you will, if you want a decimal, what is that? 3.8, 3.2. Okay. So it says order pair using integers or fractions. So I can't use the decimal. So I'm going to have to put a fraction for x is 19 over 5. Tab, comma, and the next fraction. Oh, I hate when I do that. Okay, there we go. 16 over 5. And tab, parentheses. Cool, huh? Now, watch this. Oops, wrong thing. That one. Okay. So in the calculator, there's a thing called a matrix. You guys know what matrices are? A matrix would be the matrix of coefficients. The matrix would look like this. 3 minus 2, 5, 2, minus 3, minus 2. Some people put the dotted line there to remind everybody that these are x's, these are y's, and these are constants. So we suppress the x's, the y's, the equal sign, and that's called a matrix. It's got 2 rows, 3 columns. And I can row reduce that by using the same kind of techniques we did to get here, to get rid of the x's. I could do that, and I could solve that. What we call row reduction, or I could just let the calculator do it. So this is kind of cool. So watch this. So what I do is I go into matrix and edit. And so what's how many? It says 1 by 1. Well, the rows always come first, so it's a 2 by 3. See, there's my 6 entries. I got 2 rows with 3 columns. Now I just enter those numbers. 3 minus 2. Oops, my bad. I was using the wrong, I need to use down here. Negative 2, there we go. I was using the keyboard. And then 5. And the bottom equation is 2, negative 3, negative 2. 2, negative 3, negative 2. So that's matrix A. Okay, those are the entries in matrix A. So now I just quit, and then I go to matrix math, and I go down. There's a lot of operations you can use. The one I want is right there. Row reduced echelon form, which means I want zeros above and below the main diagonal. So I only get the answers for x and y. So I hit row reduced echelon form, and then I do matrix A. That's where everything is, matrix A. And watch what happens. See, there's my answer. X equals 3.8, y equals 3.2. How about that? Now, if I said, oh, I wanted fractions, so I go math, fractions. So there it is. X equals 19 over 5. See, the way we read this now is the top line is x plus 0y. So it's x equals, there's a line here, x equals this, and this is the second column, so y equals that. See, it's got zeros above and below. So that's what we call full rank. Now, if I would have got zeros down here all the way across the bottom, then it would have been dependent. and I would have had whatever it was. If I would have had zeros across the bottom and a number here, 0 equals something, false statement. So I would have had no solution. See, the calculator does everything for us now. So this is real nice when you have three equations, 3 variables, 4 equations, because this is in the real life. This is what happens because, you know, they had to figure out how to send a man to the moon back in 1960s, late 60s, right? But they didn't have real powerful computers like this. In fact, the computers they had were less powerful than the one you're holding in your hand. And they had to come up with this linear programming. Linear programming was actually developed by the U.S. Army in World War II because they had to figure out that this was warfare like it had never been fought before. This wasn't trench warfare anymore. This was moving vast amounts of men and materials. You know, you can imagine they needed to move men, trucks, planes, gas, oil, tools, spare parts, food, latrines, blah, 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 blah. Those are all the variables. What were the conditions of the roads? How far was it? And they had to have a minimum and maximum that they could do because they didn't want to end up with the wrong things at the wrong place at the wrong time, else they wouldn't be able to fight the battle that they were planning to do. So the Army developed what they call linear programming. That's what we're going to do Thursday. And this is all leading up to it. Very simplistic on our end because we're only going to involve 2 variables rather than 3 or 4. So you can imagine when they sent a man to the moon, think of all the variables they had to deal with. Oxygen, hydrogen, weight. I can't think of all the things that they needed to do. Space, volume, you know, fuel. And they couldn't be wrong because they couldn't pull off the roadside rest and pick up something they forgot. Right?
Somebody send a tow, right?
Yeah.
Along the moon, stop along the Milky Way, get
So
gas.
they had to come up with this, and they used this linear programming. They had huge systems of equations, so many variables, and not every equation needed all the variables, but they were all in there because they were all interrelated, and they developed this system. And not only that, they didn't even know if they had the right answer when they got it all worked out because they'd never been there. There's no. I'll look at the back of the book, see what it says. You know. So what was really funny? It's a funny story. When they were doing this, they took all of the scientists that were there. They split the disciplines up, and they formed 2 teams. And the third team was the police team, because they had to keep these guys apart, because it's human nature to want to know, what are they doing? What do you think they did? Well, I know that guy, went to school with them. He'll help me out. So they had to keep them segregated so they couldn't communicate in any way, shape, or form, because they had to come up with 2 separate independent answers that were fairly close to each other so they could go ahead and say, yeah, we can get to the moon in terms of trajectory, in terms of whatever all the things that they needed to do to get there. It's really a funny story, that the lengths that they had to go through to keep these 2 teams apart and what they were doing to just get some help from each other, because it's human nature.
Yeah.
But our success getting a manned module from here, that's 250,000 miles in return. That's 250,000 miles. That's a long way. It took 3-4 days just to get there. Because I think the egress, the speed they go when they're in orbit is at least 1,800 miles per hour. That's a 90-minute orbit. That'll keep you in orbit rather than decaying and falling into the surface of the Earth. So I don't know how much more than that, how much of a bigger speed than that. It couldn't be much bigger. Let's say it was 18 or 20,000 miles per hour. 250,000 miles, that's And it's not a direct shot because you can't go to where the moon is, you have to go to where it's gonna be. So you have to go on this curve, and you're gonna meet up with it at a specific, they had to plan all this and come up with a solution that was gonna work, so this is really interesting how they use, really old computers, but the system that they devised in World War II actually carried them through. And now, with the machinery we have, calculations are like this. They can do things, on a boom, on a dime. So, anyway. So that's it for homework number 2. You guys are really on the ball. You both have finished homework number 1. And now you have homework number 2. We don't meet till Thursday. And you won't be here. Which reminds me, are you okay with meeting online? Rather than having one person here in person, I can do whatever we do on the computer. We can do it while you're at home on Kaiser Live.
That's fine, I'm okay with that.
And I can go through whatever you need to do on a whiteboard, on the calculator, on this stuff.
Okay.
And then I will. Speaking of which, I got to turn off the recording. I will go ahead and record it for Maria, so that she can view it at some point in time.
And then Monday, there's no